Hello, in this lesson we will extend what we learned about systems of linear equations in two variables to systems containing three or more variables. We will learn how to use row echelon form, back substitution, and Gaussian elimination to solve these larger systems. We will also examine systems that have no solution, infinitely many solutions, and systems where the number of equations differs from the number of variables. Let's begin by looking at our learning objectives. By the end of the lesson, you should be able to use back substitution to solve linear systems written in row echelon form, use Gaussian elimination to solve systems of linear equations, solve non-square systems of linear equations, use systems of three or more variables to model and solve real-world problems. These concepts form the foundation for future work in linear algebra, matrix methods, and many applications in science, engineering, economics, and business. Up to this point, we have focused on systems containing two variables, usually x and y. A multivariable system contains three or more variables. Common examples include x, y, and z. The goal remains the same. Find values for all variables that satisfy every equation in the system simultaneously. For example, consider the system shown on the slide. Here we have three equations and three unknown variables. Unlike two-variable systems, graphing is no longer practical. Instead, we rely on algebraic techniques such as elimination and back substitution. To prepare for these methods, we first need to understand row echelon form. The elimination method we learned earlier can be extended to systems containing more than two variables. Our objective is to transform a system into row echelon form. A system is in row echelon form when it has a stair-step pattern. Notice the second system shown in the slide. The first equation contains x, y, and z. The second equation contains only y and z, and the third equation contains only z. Because the variables gradually disappear as we move downward, the system becomes much easier to solve. Notice that both systems are equivalent, meaning they have the exact same solution. The difference is that the row echelon form is organized in a way that allows us to solve the system efficiently using back substitution. Let's see how that process works. Consider the row echelon system shown. Notice that the third equation immediately tells us that z equals 2. Once we know z, we can substitute it into the second equation. Substituting z equals 2 into equation 2 gives us y plus 3 times 2 is equal to 5, which simplifies to y is equal to negative 1. Now we know both y and z. Next, substitute these values into equation 1. Replacing y with negative 1 and z with 2 gives x minus 2 times negative 1 plus 3 times 2, which is equal to 9. And solving is going to yield x is equal to 1. Therefore, the solution is 1, negative 1, 2. This ordered triple satisfies all three equations. Notice how row echelon form allowed us to solve from the bottom upward, one variable at a time. What happens is if a system is not already in row echelon form? We use a procedure called Gaussian elimination. Gaussian elimination transforms the system into an equivalent row echelon system using row operations. There are three basic row operations. First, interchange two equations. Second, multiply an equation by a non-zero constant. Third, add a multiple of one equation to another equation. These operations do not change the solution set. They only rewrite the system into a more convenient form. Let's apply these operations to solve a system. Consider the system shown. There are multiple ways to solve it. In this example, we begin by interchanging the two equations so that the first equation has a leading coefficient of 1. Having a leading one often simplifies later calculations. Next, multiply the first equation by negative 3. Then add that result to the second equation. The x terms cancel, leaving us with a new equation involving only y. This is exactly the goal of elimination. Remove a variable one step at a time. At this stage, we have successfully converted the system into row echelon form. Now that the system is in row echelon form, we can use back substitution. From the second equation, we obtain y is equal to negative 1. Substituting y equals negative 1 into the first equation gives x minus negative 1 is equal to 0, which simplifies to x is equal to -1. Therefore, the solution is -1, -1. We verify the solution by substituting both values into the original equations and confirming that both statements are true. Now let's apply Gaussian elimination to a system with 3 variables. Our objective is to eliminate the x terms below the leading coefficient in the first column. We keep equation 1 unchanged. Adding equation 1 to equation 2 eliminates x from equation 2. Multiplying equation 1 by -2 and adding the result to equation 3 eliminates x from equation 3. After these operations, the first column has the desired stair-step structure. The system is becoming increasingly organized and closer to row echelon form. Now let's move to the second column. Our goal is to eliminate y from the third equation. Adding the second equation to the third equation removes the y variable and leaves an equation containing only z. We then divide by 2 to obtain z is equal to 2. At this point, the system is now row echelon form. Notice that this is exactly the same system we solved earlier using back substitution. Therefore, the solution is 1, -1, 2. Gaussian elimination transformed the original system into a form that made solving straightforward. Now let's examine a system that has no solution. Using Gaussian elimination, we gradually eliminate variables and simplify the equations. Eventually, we arrive at the same statement. 0 equals -2. This statement is impossible. 0 can never equal -2. Whenever elimination produces a false statement, the system is called inconsistent. An inconsistent system has no solution because no values of the variables can satisfy all equations simultaneously. This is one of the most important signals to recognize when solving systems. Now consider a different example. After applying Gaussian elimination, we eventually obtain 0 equals 0. Unlike the previous example, this statement is always true. A true statement does not create a contradiction. Instead, it tells us that one equation was redundant and provided no new information. Equation 3 depends on equations 1 and 2, and as a result, we effectively have fewer independent equations than variables. This means the system has infinitely many solutions. Let's determine what those solutions look like. From equation 2, we obtain y is equal to z. Substituting this relationship back into equation 1 gives x is equal to 2z minus 1. Since z can be any real number, we introduce a parameter. Let z equal to a, then y is equal to a, and x is equal to 2a minus 1. Therefore, every solution can be written as 2a minus 1, a, where a is any real number. Because infinitely many solutions of a are possible, the system has infinitely many solutions. Again, because infinitely many values of a are possible, the system has infinitely many solutions. A non-square system occurs when the number of equations differ from the number of variables. We may have more equations than variables, or more variables than equations. A unique solution cannot exist unless there are at least as many independent equations as variables. When there are fewer equations than variables, free variables typically appear, leading to infinitely many solutions. Let's examine an example. This system contains 3 variables but only 2 equations. Because there are fewer equations than variables, we should not expect a unique solution. First, we convert the system into row echelon form. After elimination, we obtain y minus z is equal to minus 1. Solving for y gives y is equal to z minus 1. Notice that z remains unrestricted. This means z will become our free parameter. Let's use that relationship to determine x. We substitute y is equal to z minus 1 into equation 1. Simplifying the resulting equation gives x is equal to z. Now introduce a parameter. Let z equal a, then x equals a, and y equals a minus 1, and z is equal to a. Therefore, the solution set consists of all ordered triples of the form a minus 1, a, where a is any real number. Because this can take infinitely many values, the system has infinitely many solutions. This example illustrates a common feature of non-square systems with fewer equations and variables. They often contain free variables and infinitely many solutions. In closing, in this lesson we learned how to solve multivariable systems using row echelon form, back substitution, and Gaussian elimination. We also examined inconsistent systems, dependent systems with infinitely many solutions, and non-square systems. These techniques are fundamental tools in algebra and will serve as the basis for future topics involving matrices and linear algebra. Thank you for watching, and I'll see you in the next lesson.